Okay, so it's my pleasure to introduce Kyle Broder from University of Queensland, who will speak to us today about a general Schwartz lemma for Hermitian manifolds. So please, Kyle.
Thanks, Jeff, and thanks for the invitation. Um, yeah, so today I want to talk about some very recent results concerning the Schwartz lemma for holomorphic maps between Hermitian manifolds. And the application, the main selling point will be this conjecture of Kobayashi and Lang, which which is now spanning more than 50 years, almost 55 years. So yeah, we'll see. I hope to present the most general evidence, in a sense, for this conjecture. So the results of this are based on joint work with James Stanfield, and much of this exposition is borrowed from a current work in preparation with Frederick Campana. So our model for hyperbolicity is the unit disk in the complex plane, and it has a number of remarkable properties. The first being that every holomorphic map from C into the disk is constant. The second is that there is a complete Hermitian metric on the disk with curvature bounded above by a negative constant. Perhaps the most surprising thing is that there is a distance function for which the automorphisms of the disk are isometries, and the holomorphic self maps are decreasing, or in a sense, they're Lipschitz with respect to this invariant distance function. So there's this kind of translation between, a very transcendental holomorphic type object and a very coarse, bare bones theory of distance functions, which is rather surprising. And the last property that I'll be concerned with today is that if you look at any curve whose universal cover is the disk, and you look at its canonical bundle, which in this case is just the cotangent bundle, then that will be ample in the sense that we can use the sections of some sufficiently large multiple of this to holomorphically embed the curve into complex projective space. So, of course, statement one is classical. That's just a Liouville theorem from one complex variable. The metric in statement two is just the Poincare metric of constant Gauss curvature, which you can normalize to whatever you want, but it's typically normalized to either -4 or -1. Statement three is a consequence of Pick's generalization of the Schwartz lemma, and this invariant distance function is the distance function given by integrating the Poincare metric. And statement four is a simple consequence of uniformization and the Riemann-Roch theorem. So each of these properties can be used to define a class of hyperbolic complex manifolds. So we'll say that a complex manifold is Brody hyperbolic if every holomorphic map from C into the manifold is constant. We'll use this ad hoc terminology that a manifold is negatively curved if there's a Hermitian metric with negative holomorphic sectional curvature, or holomorphic sectional curvature bounded above by a negative constant. And I'll remind everyone of the definitions here in a moment. We'll say that it's Kobayashi hyperbolic if the Kobayashi pseudo distance is non-degenerate. So this is an invariant pseudo distance that is decreasing under holomorphic maps. The definition of this Kobayashi pseudo distance is unfortunately rather ungodly, but because I'll only care about compact manifolds, we'll see in a moment that I actually don't even have to define it here. And the generalization of the fourth condition is what would commonly be referred to as being canonically polarized. So this is if the manifold is compact, we'd say the manifold is canonically polarized if the canonical bundle is ample. So the top exterior power of the cotangent bundle. So condition 1 was introduced by Brodie in 1978. The origins of the holomorphic sectional curvature are harder to pin down, but it, at least from what I can see, appears to be first introduced by Bochner in 1947. Grauert and Rexegel showed, using the Alford-Schwarz lemma, that if you have a Hermitian manifold with holomorphic sectional curvature bounded above by a negative constant, then it's Brodie hyperbolic. That's, of course, very standard now. This Kobayashi pseudo distance was introduced by Kobayashi in 1968. And as I alluded to before, the Kobayashi pseudo distance is invariant in the sense that automorphisms are isometries for this pseudo distance. And it has the property that if we have a holomorphic map from X to Y, then the pullback of the Kobayashi pseudo distance on Y is less than or equal to the Kobayashi pseudo distance on X. Now, it's not difficult to show that the Kobayashi pseudo distance on the complex line vanishes identically. And so if we suppose that we have a holomorphic map from C to X, which is non-constant, then by pulling back the Kobayashi pseudo distance on X, we get this inequality here. And so we have the contrapositive statement of 3 implies 1. So we know that Kobayashi hyperbolicity is always stronger than Brodie hyperbolicity. Now, the remarkable thing that motivated the definition of Brodie hyperbolicity is the main theorem in the same paper, where Brodie shows that if the manifold is compact, then 1 and 3 are equivalent. So I don't have to speak about non-degeneracy of the Kobayashi pseudo distance. I can just say that every holomorphic map from C to X is constant. Now, the Alford-Schwarz lemma argument does not show that 2 implies 3. There doesn't seem to be a clear way of getting it directly in that way, but Green Wu were able to show a few years later that 2 does imply 3, and they do that by estimating the Kobayashi pseudo distance from below directly. This is much more elaborate than a standard Alford-Schwarz lemma argument. Now, just as a reminder, the canonical bundle is ample, as I said before, if the sections of some sufficiently large tensor multiple of the canonical bundle provide an embedding of X, holomorphic embedding into some complex projective space. And these manifolds are particularly nice because we have access to the methods of algebraic geometry, because they're all projective by definition, and we have a vast number of techniques and tools available to us. On the other hand, it's clear that condition 4 is the weakest, in the sense that we consider a Fermat hypersurface of sufficiently large degree, then this will have rational curves. So holomorphic maps from P1 to X, and in particular, we'll have holomorphic maps from C into X. So it won't be hyperbolic in any of these other senses. Now, if you haven't seen these before, it can be kind of hard to keep track of all these various implications. So here we just have a diagram to recall all of these. But the main one we're going to be concerned with is perhaps the implications that are missing in this diagram. So the main purpose of the present talk is to present, in a sense, the most general evidence for the following conjecture of Kobayashi and Lang. They conjectured this independently. And that's the following. The prediction is that if we have a compact Kobayashi hyperbolic Kähler manifold, then the canonical bundle is ample. Now, I assume everyone is familiar with Kähler, but in the off chance that we've forgotten, a Kähler manifold is a complex manifold which admits a Hermitian metric for which this 2 form given by plugging J into the first argument is closed. And I'll comment, I'll try to comment later on exactly why we assume compact scalar in this conjecture. Now, a positive resolution of the Kobayashi-Lang conjecture has a number of important consequences. So the first is that all compact Kobayashi hyperbolic manifolds are projective, at least if they're scalar. And that means that they can be studied using algebra or geometric techniques. But at least from the differential geometric point of view, one of the remarkable things is that if you have no holomorphic maps from C to X, then the Orban-Yau theorem tells you, well, as a consequence of this conjecture, you have a Kähler-Einstein metric of negative Ricci. So it gives you a sufficient condition for an Einstein metric of negative curvature. So if we I'm not assuming that everyone is 100% familiar with Kobayashi hyperbolic manifolds, so should just give a couple of examples. Again, I want to stress that the definition that I'll take here is really Brody hyperbolicity, but I will just write Kobayashi hyperbolicity because that's a bit more standard. Main examples one wants to have in mind are perhaps compact quotients of bounded domains in Cn. So in particular, if you have a curve of genus, topological genus, at least 2 will be Kobayashi hyperbolic. If one takes a generic smooth hypersurface of sufficiently large degree, and the best bound appears to be the following, so d bigger than or equal to 16 n cubed with 5n plus 4, that appears to be the best bound that we have so far. That will be Kobayashi hyperbolic. This is due to this 2023 result, and this answers a long-standing conjecture of Kobayashi himself, which says that if you take a generic smooth hypersurface of degree sufficiently large, depending only on the dimension, then it should be Kobayashi hyperbolic. And that was first resolved by Siu and Brotbeck, and then effective results where the lower bound was actually given explicitly were later given by Deng, Demailly, and others. An important source of generating examples comes from the fact that Kobayashi hyperbolicity is inherited by products, submanifolds, universal covers, and fiber spaces. Now, when I say something is preserved or inherited by fiber spaces, I mean that if the base and fiber are Kobayashi hyperbolic, then the total space is hyperbolic. And a fiber space will always be understood to mean a surjective holomorphic map with connected fibers. So not necessarily a submersion. Okay. And one of the things I find very interesting about this Kobayashi-Lang conjecture and its folklore generalization, which is what I mean by that is if you drop the Kähler assumption, it's still widely believed to be true, then the techniques vastly diverge depending on what additional assumptions one places on the manifold. So for instance, one can place assumptions on the canonical bundle itself, for instance, assuming the canonical bundle is big or pseudo-effective or something, and then the techniques are largely algebraic. Then if one only wants to consider the Kobayashi-Lang conjecture for surfaces, the focus is on producing rational curves on class 7 surfaces with second Betti number at least 3. The only case to rule out is the potential for non-Kato class 7 surfaces. Of course, if we had the global spherical shell conjecture, that would resolve the Kobayashi-Lang conjecture and its folklore generalization in dimension 2. On the other hand, if we look at threefolds, looking at a non-projective or non-Kähler threefolds is largely out of reach without any additional assumptions. So here the focus is largely on Kähler threefolds or projective threefolds. And here the focus is on ruling out the hyperbolicity of Calabi-Yau threefolds, which I'll which I'll explain in a moment. And here the focus is particularly on understanding the geometry of the Kähler cone of Calabi-Yau threefolds with second Betti number less than or equal to 13.
Sorry, Kyle. Will you explain what you
Yep.
mean by this folklore generalization? I guess eventually.
By folklore generalization, I mean a compact
removing
Kobayashi
Kähler, or-
hyperbolic manifold
Yeah.
without any Kähler assumption
Yeah,
is
without Kähler.
has ample canonical bundle. Yeah.
Okay.
Yeah, that's so. I can speak about that a little now. There's I spoke with Campana about this. This is actually what led to the current project with him. I wanted to know if there was anything in the air at the time of these when these conjectures were made, if there was an example one had in mind. From what I understand, there's a generally strong belief that Kobayashi hyperbolic manifolds should be projective with ample canonical bundle. Like they can't have negative Kadara dimension, things like this. But there's no general structure theory for non-Kähler manifolds. There's no, even conjecturally.
Right.
And so it's just people are a bit more sheepish. They don't want to be so bold and say that such a conjecture is true, but it's strongly believed, at least from what I've gathered. So yeah, okay. And the last aspect, which will be the primary focus of the present talk, is looking at this conjecture under curvature assumptions. And the main focus in this direction is on removing the presence of a Kähler structure. So I'll explain that in greater detail later. So let's just start with some reminders. So if we have a compact Kähler manifold X, then the Kähler cone is the open convex cone of cohomology classes in H11, which are represented by the Kähler form. And the closure of the Kähler cone defines what's called the Neff cone. Now I have this very nice picture of a Kähler cone. It's a very specific type because it's obviously polyhedral here and whatnot. They don't always look like this, but this is sufficient for our purposes here. I won't be speaking about any results, at least regarding the curvature stuff, which depends on the structure of the Kähler cone. And so here the canonical bundle will be ample if the first Chern class of the canonical bundle is in the interior of the Kähler cone. And if one prefers a more curvature interpretation of this, then by the Orban-Yau theorem, this is equivalent to the Kähler-Einstein metric of negative Ricci curvature. On the other hand, if we can understand the canonical bundle to be Neff if the first Chern class is in the closure of the Kähler cone. And this is equivalent to the Kähler-Ricci flow existing for all time by a result of Tian and Chang. Okay, so in 82, Mori showed that a projective manifold with no rational curves, namely if every holomorphic map from P1 to X is constant, then the canonical bundle is Neff. So this was extended to compact Kähler threefolds by Oring and Peter Nell in 2016. And so for these class of manifolds, if we assume it's Kobayashi hyperbolic, then the canonical bundle is automatically Neff. So that's an important stage towards ampleness. We're on the boundary of the Kähler cone. Now, if we assume the Kähler extension of the abundance conjecture, then if we know that Kx is Neff, then it's actually it satisfies a stronger condition, namely it's semi-ample. And this means that the sections of some sufficiently large multiple of the canonical bundle give X the structure of a fiber space. So there's a surjective holomorphic map with connected fibers. And I'll explain the structure of this fiber space more in a moment. And we know this for projective manifolds of dimension less than or equal to 3, and for Kähler manifolds of dimension less than or equal to 3, modulo a rather technical there's a slight gap from what I understand in the Kähler extension result. So this fiber space here I'll refer to as the Itaka map, and the smooth fibers of this Itaka map are compact Kähler manifolds with holomorphically torsion canonical bundle. If X is projective, then these will be projective manifolds with torsion canonical bundle. So some sufficiently large multiple of the canonical bundle will be trivial. And the base is a normal projective variety that's irreducible and reduced, whose dimension is the Kodaira dimension of X. So if X is a compact Kobayashi hyperbolic manifold with maximal Kodaira dimension, so Kodaira dimension equal to the dimension of the manifold itself, then the Itaka map is a bimeromorphic map, and so X is in particular a Moishezan manifold, so bimeromorphic to a projective variety. And since Kobayashi hyperbolic manifolds have no rational curves, we know from the results of Burker, Kashini, Haken, and McKernan that X is actually projective. Now one can use some big results from algebraic geometry, namely the base point free theorem and relative cone theorem, to then deduce that the canonical bundle is ample. And so in particular, we have that a compact Kobayashi hyperbolic manifold, maximal Kodaira dimension, has ample canonical bundle. So phrased another way perhaps is that a compact Kobayashi hyperbolic manifold of general type has ample canonical bundle. And this seems to have been first observed by Xiaoque Yang in 2020. Now, if we have X projective and Kobayashi hyperbolic, and we assume the Kodaira dimension is less than the dimension, so it's not maximal, then in this case, we have an Itaka map with positive dimensional fibers. And since Kobayashi hyperbolicity is preserved by submanifolds, it suffices to rule out the hyperbolicity of the smooth fiber. So we want to rule out the hyperbolicity of projective manifolds with holomorphically torsion canonical bundle. And for this, we can actually just rule out the hyperbolicity of its universal cover, and we have rather strong structure theorems for such manifolds. So we know that the universal cover of a compact Kähler manifold with holomorphically torsion canonical bundle splits as a product of Euclidean, Calabi-Yau, and hyper-Kähler factors. This is, of course, the Bogomolov-Beauville decomposition theorem. And the splitting, of course, the Euclidean factor will not be hyperbolic. So we really only have to rule out the hyperbolicity of Calabi-Yau manifolds and, of course, the hyper-Kähler manifolds. So here, because, if you want to confuse anyone in a complex geometry seminar, you just have to say the words Calabi-Yau and not define it. So here's exactly what I mean by Calabi-Yau. So it's a simply connected projective manifold with holomorphically trivial canonical bundle, and the only non-zero holomorphic forms occur in degree 0 and degree n, where n is the dimension. Now we understand hyper-Kähler to mean a simply connected compact complex manifold with holomorphic forms, the algebra of holomorphic forms being a polynomial algebra in this non-degenerate holomorphic 2 form. That's why they're often referred to as irreducible holomorphically symplectic manifolds. Now, it's a result of Verbitsky in 2015 that hyper-Kähler manifolds with second Betti number bigger than 3 are not hyperbolic. And it's conjectured that all hyper-Kähler manifolds satisfy this lower bound on the second Betti number. So modulo this conjecture, that would rule out them. In dimension 3, however, one does not have to consider these because hyper-Kähler manifolds are the dimension is a multiple of 4. So the universal cover of a Calabi-Yau threefold, threefold with holomorphically torsion canonical bundle will be a Calabi-Yau threefold if it's hyperbolic. The non-hyperbolicity of the Calabi-Yau surfaces, namely the K3 surfaces, was shown by Wong in 81 and by Campana in 91 independently. And there's been a wealth of results concerning the hyperbolicity, or ruling out the hyperbolicity of Calabi-Yau threefolds. And they are largely technical results concerning the geometry of the Kähler cone, but perhaps one of the most important results is that the second Betti number will have to be less than or equal to 13. And that comes from results of Heath, Brown, and Wilson, which show that if you have a Calabi-Yau threefold with second Betti number bigger than 13, then it actually has an elliptic fiber space structure and therefore cannot be hyperbolic. And just one last comment in this direction. If the Kawamata-Morrison-Cone conjecture holds, then which predicts that up to some action of an automorphism group and whatnot, the Kähler cone is polyhedral, then it would actually constrain the second Betti number of a hyperbolic Calabi-Yau threefold to be equal to 1. So De Virio showed that in a small 2013 paper. Fortunately, this is not a specific case. B2 equal to 1 is satisfied by a large number of manifolds, so it's not terribly restrictive, unfortunately. Okay. So concerning the folklore generalization, just to reiterate something that I said before, if we look only in the context of surfaces, then we know from the work of Bogomolov, Li Yao Zheng, and Tillerman that a compact complex surface of class 7, minimal class 7, if it was hyperbolic, would have to have second Betti number bigger than or equal to 3. That's because we know that we have a classification of the minimal class 7 surfaces with B2 equal to 0, 1, and we have a cycle of rational curves if the second Betti number is 2. Now, if we had an answer to the global spherical shell conjecture, then we would know that a minimal class 7 surface would have B2 rational curves, and so in particular wouldn't be Kobayashi hyperbolic. So that's what remains in the dimension 2 story. Okay, so I'm now at the main point of what I want to focus on today. So, of course, I assume everyone is familiar with this, so let me just have a quick reminder. So we have X as a complex manifold. I have a Hermitian metric, which is locally described by a locally defined Hermitian matrix, like in this way. I have the Chern curvature tensor, so the curvature tensor of the natural Hermitian connection associated to G. That'll be the 0,4 tensor whose components are locally given by minus the Hessian plus this first order term. And the main the main curvature constraint I want to worry about today is this holomorphic sectional curvature, which one can think of. Let's say you have a Kähler metric, you could restrict the sectional curvature to the 2 planes which are invariant under the complex structure, and that would recover this holomorphic sectional curvature here. Okay, so I'll be primarily, almost exclusively concerned with manifolds with negative holomorphic sectional curvature, and unfortunately these are not too easy to come by, but important examples to have in mind are the Bergman metric on compact quotients of a bounded symmetric domain. A wealth of examples are given by submanifolds, products, and it's also preserved by submersions. So this is a result of Chung, that if you have a holomorphic submersion such that the base and fiber have negative holomorphic sectional curvature, then the total space will also support such a metric. A very interesting mechanism for generating metrics of negative curvature was recently given by Mosen in 2022. He shows that if you have let's suppose you have a projective manifold of dimension n, and you suppose that n is bigger than 3D, then for every sufficiently large k, you can find a complete intersection y of dimension d defined by degree k equations, which has negative holomorphic sectional curvature. And so this uses some very fancy machinery, this Donaldson-Aurot theory, and it not only produces metrics of negative holomorphic sectional, but it determines conditions for negative bisectional, negative Ricci, negative scalar, and so forth. It's a very interesting paper. It's important to, in terms of understanding the strength of the holomorphic sectional curvature, if the metric is scalar, then the holomorphic sectional controls the sign of the scalar curvature. But in general, it only dominates the sum of the scalar curvatures. So of course, there are two Chern scalar curvatures given by tracing in the two different ways. And the holomorphic sectional does not control the sign of either of them, but it controls the sign of the sum of them. In fact, if it's a pluriclosed metric, one can show that negative holomorphic sectional implies negative of this altered scalar, while positive holomorphic sectional would imply positive of the ordinary Chern scalar. I don't know if that's a well-known result, but it's rather elementary to show in the case of a pluriclosed metric. So there's another very important example to have in mind is that the holomorphic sectional curvature certainly doesn't control the sign of the Ricci curvature, because it was shown by Hitchin that the Herzebrück surfaces all have Kähler metrics of positive holomorphic sectional curvature, but most of them, if n is bigger than 1 here, none of them will have positive Ricci curvature. So it's definitely not strong enough to control the Ricci. Okay, so if we restrict the Kobayashi-Lang conjecture to the context of, well, in the presence of these additional curvature assumptions, then this is also a conjecture of Yau. So around the 70s as well, the origins are a bit hard to pinpoint. So he conjectured that a compact Kähler manifold with a Hermitian metric of negative holomorphic sectional has ample canonical bundle. It's important to acknowledge that this is a non-exhaustive case of the Kobayashi-Lang conjecture. Indeed, Demailly showed that not every projective Kobayashi hyperbolic manifold has a Hermitian metric of negative holomorphic sectional. He constructs a projective surface, which is fibered by hyperbolic manifolds over a hyperbolic base. But then one of the fibers is so singular that it violates an extension of a Riemann-Hurwitz type theorem, which he proves in this same paper. So there's, in a sense, a kind of sensitivity to the singularities of the curves inside the manifold that is detected by the holomorphic sectional that's not detected by hyperbolicity. And it's also perhaps worth noting that this seems to be the only obstruction to the existence of a negatively curved metric on a hyperbolic manifold. So I'm not aware of any other constraint or obstruction. Okay, so in terms of the reason why this conjecture in particular has achieved so much attention begins with this work of Haya, Liu, and Wong. So they showed that if you had a projective threefold with a Kähler metric of negative holomorphic sectional curvature, then the canonical bundle is ample. So here we make use of Maury's theorem and abundance and whatnot. Wu Yao later developed a general strategy to show that projective manifolds of any dimension with a Kähler metric of negative holomorphic sectional curvature have ample canonical bundle. Again, we're still using a Maury theory here to get Neff-ness of the canonical bundle, but the general strategy set up by Wu Yao is still the strategy that will be used here. The projective assumption and therefore the use of Maury theory was overcome by Tosati and Yang a year later. So they're able to relax projective to compact Kähler. And then a Kähler-Ricci flow argument was given by Nomura in 2017 as well. Okay. So let's outline this Wu Yao strategy. So the key point is to use the Kähler cone to produce a sequence of metrics whose Ricci curvature is bounded from below. So how does one do it? Well, we'll present the argument to show that the canonical bundle is Neff, and then essentially the same argument goes from Neff to ample. So we'll do the Neff case first. So this is really due to Tosati and Yang. Proceed by contradiction and suppose the canonical bundle isn't Neff. So the first Chern class is not contained in the closure of the Kähler cone. Now, because the manifold is Kähler, I have some Kähler metric omega 0 lying around, and the cohomology class represented by that metric will be in the interior. And so if I look at the line which connects them, I can eventually, I can find the intersection with the boundary of the Kähler cone. So there'll be some positive epsilon 0, such that epsilon 0 times this cohomology class of the metric plus the first Chern class of the canonical bundle is on the boundary of the Kähler cone and not in the interior. But then for any positive epsilon, I bump myself back into the Kähler cone. And so now I have a Kähler class, a cohomology class represented by a Kähler metric. And so by the Orban-Yao theorem, I can now produce Kähler metrics which solve this complex Monge-Ampere equation. So here the Ricci curvature, if this was a Hermitian metric, this would be first Chern Ricci. The Ricci curvature represents this first Chern class, and so I have this sequence of Kähler metrics depending on epsilon, which satisfy this Monge-Ampere. Okay, so if I then differentiate this Monge-Ampere equation, so I take IDD bar log of both sides, we see that we get the Ricci curvature of omega epsilon is minus IDD bar U epsilon plus Ricci of the background metric. But from the definition of omega epsilon, we get this kind of, twisted Einstein type condition. So we get a sequence of metrics with Ricci curvature bounded from below in this sense. Now the key point to this argument is to use the negatively curved metric, which has not appeared yet, to get to compare with these flowing metrics and obtain higher order estimates to all orders, and then extract a smooth limit as epsilon goes to 0. So what will that do? Well, that'll give us a Kähler metric representing this cohomology class here, but we assume this is a Neff non-Kähler class to begin with, so that gives us the desired contradiction. Now, how one does this is in a sense standard. You kind of, the crux of the argument is to get the estimate on the trace, and then one uses the equation to get the other side, and then one uses kind of Calabi-Nirenberg type techniques that decades old now to then get the higher order estimates. And so the real difficulty is this trace estimate here, a uniform estimate on this trace independent of epsilon going to 0. Now this trace estimate is exactly what I'll call the Schwarz lemma. And there's at no point where I have to use a holomorphic map, which is different from the identity, but the formulas look more confusing if I take the identity map. So I just like to use an arbitrary holomorphic map. Okay, so now we're going to get into the meat of this result. So I'll always have F as the identity map, as I said just then. The derivative of this map is locally described in this way. So I'll write Fi alpha for the ith derivative of the alphath component. And I'll denote by G the metric underlying omega epsilon, and by G hat the metric underlying omega hat. Now, in 1967, a very old calculation, Liu showed the following. Liu showed that if you take the Laplacian of the trace, both with respect to G of the pullback metric, you get 3 terms. You get this second fundamental form type term, or the pointwise square norm of the second fundamental form. You get this source curvature term, which is dependent on the Ricci curvature of G. And then you get this target curvature term, which is a bit more difficult, which is depending on the target curvature metric, or the target metric, sorry, so the G hat metric. So in particular, if I want to apply the maximum principle to this, I have a compact manifold, so I don't have to worry about any maximum principle difficulties. We want to have a lower bound on this Ricci curvature term of G, and we want to have an upper bound, preferably a negative upper bound, on this target curvature term of G hat. Okay, so since Liu's calculation in 67, there have been 2 general improvements. Now here I'm being rather precise in the sense that I'm not saying that no one has done anything since Yau or Royden. I'm not saying that at all. I'm saying that if one just looks at this calculation itself and looks at trying to improve this calculation, not depending on a Monge-Ampere, not depending on some tricks that's very specific to a problem, there have not been many improvements on this. We've really only had 2. And those appear more or less at the same time. So the first one is Yau's contribution. So Yau applies his generalized maximum principle to this calculation, which allows for non-compact source manifolds with a Ricci curvature lower bound. Of course, that's not particularly relevant here because we already have compactness. But for us, this result of Royden is the main deal, which shows that the target curvature term is controlled from an upper bound on the holomorphic sectional if the metric is Kähler. Now it's, of course, kind of well known now that this Royden argument only requires the symmetries of the Kähler curvature tensor, so it actually works in slightly greater generality of Chern Kähler-like metrics, which were introduced by Yang and Zheng in 2016, but we don't have any really non-trivial examples except flat ones of Chern Kähler-like metrics. So it's still due to Royden in a sense, though, because it's just making sure that Royden's technique works. So these are really the only improvements we've seen in this level of generality. But if we look at Royden's Schwarz lemma for the moment, so we assume that G hat is a Kähler metric, and it has a non-positive upper bound on its holomorphic sectional curvature. Then we end up with an upper bound of this type. So here n is the dimension of the manifold, and we have it's important. I mean, experts will know that it's important that this is a square, but if that means nothing to you, do not worry about it. So this is Royden's Schwarz lemma. This is the one that is responsible for many of these results. So we have a compact complex manifold, dimension n. I look at a holomorphic map from X to itself, take it to be the identity map. You won't lose anything there. Suppose you have a Kähler metric with this type of lower bound. This lower bound has some history. Various people introduced various generalizations of this lower bound. Royden didn't have this C2 term, for instance. Now, suppose you also assume the target metric is Kähler with non-positive holomorphic sectional. Then you end up with an estimate that is like this. So you have this C2 term battling with or potentially contributing together with this upper bound on the holomorphic sectional, and then this C1 is kind of harmless in a sense. And this second fundamental form term is completely harmless. I mean, it's non-negative. It's a very good term. So as a consequence of the maximum principle, we then just get by basic algebraic manipulation this estimate on the trace. Now, in the Wu-Yao theorem, we have these conditions. We have C1 is equal to 1 in this case, and C2 is epsilon plus epsilon 0. So we end up getting the following. And in particular, it's uniformly bounded as epsilon goes to 0. So this is the only place really where this negatively curved metric appears in the results. So the Schwarz lemma gives us this upper bound. It's not difficult and is standard to get a lower bound by using the equation itself. And then establishing higher order estimates is again standard. It's quite old. It goes even as back to Calabi, Nirenberg, and whatnot. It's done in great detail by Tassati and Yang. But that's not our issue. The issue is mainly this Schwarz lemma estimate. So once we have these higher order estimates, we can let epsilon go to 0. And then, as I said before, that will contradict the fact that the canonical bundle is we assume the canonical bundle is not Neff. And when we take this limit, we have a Kähler metric representing a non-Kähler class, and that's how we get the desired contradiction. And as I alluded to before as well, the same argument shows that if you assume Kx is Neff but not ample, then the same procedure gives you ampleness under the assumption of strictly negative holomorphic sectional curvature. Okay, so I want to one of the main points of this talk is to really lay it out very clearly where this Kähler assumption is used, because we want to, I'd like the folklore generalization of the Kobayashi-Lang conjecture. And so we want to just make it very clear where these Kähler conditions are appearing. The first is kind of obvious, to set up this complex Monge-Ampere equation. We use a definition of Neffness that, although Neff can be defined on an arbitrary compact complex manifold or complex manifold, the particular definition that we've used to set up the Monge-Ampere, the generalization of that does not give you the Monge-Ampere. It's much more awkward to deal with. If you assume that Kx is not Neff in the general sense, it doesn't pan out. It just kind of doesn't lead to anything useful. The second major problem is in equating the Chern-Ricci curvatures of the source metrics or the flow metrics. So the Monge-Ampere equation, even if you had one, it only controls the first Chern-Ricci curvature, so the one given by tracing over the third and fourth indices. But the Ricci curvature that appears in the Schwarz lemma is the second Chern-Ricci. the one that you get from tracing over the first two. And it's very difficult to, I don't think we know much at all about how to control the second Chern-Ricci from the first Chern-Ricci. And the third condition is somewhat clear, and that's in order to apply this Royden's-Schwarz lemma. And that's the only case where the Kähler assumption is used on the target metric or the negatively curved metric. So, okay, so in the Wu-Yao theorem, as I mentioned, this target curvature term is controlled by the holomorphic sectional if it's Kähler, and that's as a consequence of Royden's argument. For non-Kähler metrics, Royden's argument fails, it breaks down entirely, or for non-Kähler-like metrics. And so as a consequence, Yang and Zheng, they introduced this real bisectional curvature term. So here, these xi are non-negative Hermitian 1-1 tensors, which in Jeff's paper with Manchun is referred to this complex curvature operator. And this curvature condition is defined precisely to control this target curvature term. I mean, that's the role it is used in and motivated by exclusively in the Yang-Zheng paper. Now, as a consequence of it being defined in this way, you kind of get a straightforward extension of the Wu-Yao theorem. So if you have a compact Kähler manifold with a Hermitian metric of negative real bisectional curvature, then the canonical bundle is ample because you've dealt with the third obstruction that I listed before. But it's known, Yang and Zheng show that the real bisectional curvature is stronger than the holomorphic sectional. And so what we're left with is this kind of we're getting how are you supposed to improve this calculation? I mean, they literally defined a quantity that is the target curvature term. Well, I mean, you're literally at a roadblock. There's no chance of making any improvement. And so the real surprising thing is that yes, you can make an improvement. So this is one of those things that kind of you spend 2 years doing very gory calculations, and then you kind of do this you make this elementary observation, and then it turns out that everything falls out of these kind of elementary observations. So it turns out the real bisectional curvature is not sharp. One can do a trick here, and this will be the new Schwarz lemma that I will talk about. But before I present this more technical result, this is the main application. So this appears in the recent paper with James Stanfield. We're able to show that if we have a compact Kähler manifold, so some Kähler metric lying around, and we assume that we have a pluriclosed metric of negative holomorphic sectional curvature, then the canonical bundle is ample. So this is, in a sense, the first honest generalization of Royden's technique. So we're not attempting to hijack Royden's old argument, but we're able to get an honest class of non-Kähler Hermitian metrics and extend the Schwarz lemma in that way.
But is the main point that like that these two conditions on G hat, the pluriclosed and the holomorphic sectional curvature negativity, lets you control the term, and it gives you a sign for this term? That's the point.
Yeah.
That's somehow the original argument used symmetries coming from the Kähler condition.
Yeah. So Royden's argument,
you get away with something.
Exactly. Yeah. So Royden's argument fundamentally requires the symmetries of a Kähler metric. You can't well, you can get Kähler-like, but nothing else will satisfy the conditions that Royden needs. And the point is that we are able to control this if the metric is pluriclosed with a holomorphic sectional curvature upper bound. Because in a sense, I mean, Yang Zheng laid it out very clearly. I mean, if it's not a Kähler-like metric, the holomorphic sectional won't cut it. And so that's the kind of surprising thing here. So, okay, so of course I assume everyone is very familiar with this, but just to remind ourselves, a Hermitian metric is pluriclosed if it satisfies this generalization of the Kähler condition, namely that not that d omega is zero, but dd bar of omega is zero. We know, of course, that such metrics always exist on compact complex surfaces by an old result of Gordachon. And one other rather interesting observation is if we look at this Wu-Yao theorem and look at the, let's suppose you want to have a condition on the background metric, then it doesn't really give you much in terms of the Schwarz lemma because you don't apply the Schwarz lemma to the background metric, you apply the Schwarz lemma to this sequence of metrics. And so the Kähler condition is preserved by this map that sends the initial metric to this, perturbation by the Ricci and whatnot. But the only other one that I can think of that satisfies this as well is the pluriclosed condition. So there's a lot of places where the pluriclosed condition is relevant, which I think is worth exploring, but I mean, it's still a mystery at the moment. Okay, so let me now present this general Schwarz lemma. So I suppose that I have a holomorphic map between Hermitian manifolds, and then for a positive constant tau, which I'm free to choose, we have the following inequality, that if you take the G Laplacian, the G complex Laplacian of the trace of the pullback, then we get the same terms as before. We get the second Chern Ricci acting on this object here, and we get the bisectional curvature term appearing. But we also get these quadratic torsion terms coming out. And the idea is actually very simple. You'll notice that the second fundamental form term I've gotten rid of. So what we do is we use I could have kept the symmetric part of the second fundamental form term, but I might as well get rid of it entirely. If you look at the skew symmetric part of the second fundamental form term, if the metrics are Kähler, that doesn't give you anything. But if they're non-Kähler, you end up getting torsion, precisely these torsion terms. And then this tau factor is just coming from a, Cauchy-Schwarz or, Young inequality type thing. So it's a very simple argument, which took 2 years to discover. But what's kind of very interesting is that, okay, if you have the source metric being a Kähler metric, I can actually do a lot better. I can take tau to be 0, because this thing that blows up, I mean, that's not even present because the Q2 is 0. And then what we end up getting is this real bisectional curvature term, but it's kind of tempered by this quadratic torsion. And so naturally we called this the tempered real bisectional curvature. Of course, this terminology, or this notation, I should say, is suggestive, because this is precisely the quadratic torsion term that appears in the Ustinovsky flow. But there's this terrible factor in front of it. So this tempered real bisectional curvature is actually intrinsic to the Hermitian structure, in the sense that if you look at the Hessian of the metric in the geodesic normal coordinates for the Chern connection, you get this term out. There is a quadratic torsion term error with the curvature. So I'm not going to claim that this is indicative of it being sharp, but it seems to be a natural condition to introduce. And perhaps the biggest motivator is that, remarkably, if the metric is pluriclosed and even if I have this 1 minus tau factor still there, and tau is sufficiently small, negative holomorphic sectional curvature implies negative tempered real bisectional curvature. And this just uses an elementary curvature identity that all pluriclosed metrics satisfy. So it's two basic ingredients, but it leads to this very significant generalization. So let's give a formal statement of this main result. So the statement would be that we have a holomorphic map from a, let's say, compact scalar to a pluriclosed manifold. We suppose that the Kähler metric satisfies this Ricci curvature lower bound, and the holomorphic sectional of this pluriclosed metric is bounded above by a non-positive constant. Then what you end up getting is precisely what you would with the Royden-Schwarz lemma. And so as a consequence, by the maximum principle, you end up with this upper bound on the trace. And so because this was the only obstruction to the generalization, we were able to show that if you have a compact Kähler manifold with a pluriclosed metric of negative holomorphic sectional, then it has to be projective with ample canonical bundle. So the Wu-Yao argument goes through verbatim. So now I want to talk about the kind of bits I can't do. So as I mentioned before we started, in my opinion, one of the most significant achievements in this direction is due to Jeff and Manchun, where they use the pluriclosed flow to establish the following result. So they show that a compact pluriclosed manifold with a Hermitian metric of negative real bisectional curvature has ample canonical bundle. So they bypass the Chern-Ricci comparison, and they bypass the Kähler-Cohn argument. And it should be emphasized that the only way to bypass those is through a geometric flow. That's the only known method to handle it. So naturally, given it's almost frustrating to see this theorem and then not see, okay, you have a pluriclosed negatively curved metric, surely these two can just go together, just use the pluriclosed flow. So that's what we tried to do. So we have this parabolic extension of the tempered Schwarz lemma, and we know that if we have a family of Hermitian metrics which sub-solutions of this type of Hermitian curvature flow for tau sufficiently small, and we have a pluriclosed metric with let's say negative holomorphic sectional, then you get this parabolic Schwarz lemma calculation. And this applies to, let's say, the second Chern-Ricci flow. The second Chern-Ricci flow is an example of a flow that will satisfy this, but the pluriclosed flow or even the Ustinovsky flow will not. And so this
sorry,
is
can
the
I
main
ask,
issue.
in that result, you're taking tau small relative to lambda naught, I guess? Or what's the smallness on tau?
So I require tau to be small so that the holomorphic sectional being negative implies the tempered real bisectional is negative.
Yeah. Okay.
Yeah.
Okay.
So that it's independent of the lambda zero.
Mm-hmm.
Yeah. Yeah, so it doesn't have to be, it doesn't have to be zero, but it does have to be quite small. This is just more of an algebraic argument in a sense. But okay, so we want to understand this compatibility with the pluriclosed flow. Like this is one of the goals. So just to give all the technical details, the pluriclosed flow has this quadratic torsion term. So the quadratic torsion term has the indices in the first two parts of the torsion. And if we attempt to apply the parabolic tempered Schwartz lemma to the pluriclosed flow, you end up with this. So you have, now you want to bound this from above. So this term is the bad one, because if tau is very, very small, this is very, very big. And so usually you just get rid of this Q1, but we keep it in because maybe there's a chance to deal with these terms together. And so this bad term, if that's the one that can be dealt with, then it would lead to the very satisfying result that a compact complex manifold with a pluriclosed metric of negative holomorphic sectional has ample canonical bundle. That would be very, very satisfying. But this term here is precisely the obstruction.
I guess maybe I just mentioned in other places in pluriclosed flow, you have to sort of estimate some bad positive torsion squared term. And oftentimes the trick is to incorporate this beta field. So basically you have something like a potential for the torsion where basically the difference of del omega from a background del omega is d bar beta for a 2-0 form beta. And the norm squared of that 2 form satisfies some very good, well, some good evolution equations, but there are background terms. But in particular, it gives a term which can control the torsion, maybe in principle. So if it were me, I would try to. I suppose the hope is that with this special background metric, that somehow maybe those terms can be controlled. Like there's really just kind of one bad background term involved. But actually, it's in any case, maybe we can talk about it after. But,
yeah. Absolutely. This is exactly why I presented it so thoroughly. But I mean, this is what I wanted to finish with, so I think I'll stop there anyway. Thank you.
Okay, great. Yeah, thanks. Yeah, very interesting.